Hello guys, this is Gautam Sathik and welcome to my channel. Today I am going to teach you potential energy. In physics, potential energy is not defined. In physics, potential energy is not defined. Only change in potential energy is defined. That too, change in potential energy is only defined for conservative forces. For non-conservative forces, change in potential energy is not defined. For non-conservative forces, it is only defined for conservative forces. And this potential energy is not defined for a single body. It is defined for a system of particles, at least two bodies. And the change of potential energy is nothing but negative work done by conservative forces. We must not include all the forces, we must include only conservative forces. Change in potential energy is nothing but negative work done by conservative forces. That means we can write this as this is conservative force. You know the work formula, right? This is, now I'll write potential energy as U. Now it becomes du, small change in potential. Now this is the formula for change in potential energy. You must integrate it on both sides from U initial to U final. This from x1 to x2. This is the formula for change in potential energy. Remember that potential energy is not defined. Only change in potential energy is defined. That change in potential energy is only defined for conservative forces. It is not defined for non-conservative forces. And potential energy is only defined for a system. It is not defined for a body, a single body, right? Copy this. Now I'll give you a numerical. Pause the video and try it yourself until you get the answer. Given a force, a conservative force, 3I cap plus 4J cap is acting on a body. Given potential energy at 0,1 as 10 joules. Now we were asked to find the potential energy at 2,3. This is a conservative force. Now pause the video and try it on yourself. At least for 10 minutes, try it on yourself. Now we know that change in potential energy is negative work done by conservative forces. Now here we are given x as well as y. So let us divide this as minus force in x direction, force in y direction into displacement in y direction. This is du. From this is integrating this, we get this is from 10 to let this be x. We must find x, right? X. This is nothing but x minus 10 is equals to Fx, force in x direction. What is it? 3. Now we must integrate this even 3 dx minus 4 force in y direction dy. Now from where to where should we integrate this? See, in x direction it is moving from 0 to 2 and on y axis it is moving from 1 to 3. So we must integrate this from 0 to 2 and this from 1 to 3. and that's it, your job is done. This is a mathematics problem now. Now this is minus 6 and minus 8, right? Is equals to x minus 10. Bringing 10 to this side, we'll get x as minus 4 joule. No. Now here the potential energy is minus 4 joule. Got it? Now let us discuss about types of potential energy. In class 11 we will be dealing about gravitational potential energy and spring potential energy. Gravitational potential energy. Now, if a body, look at, this is M1 and this is M2, separated by distance r, then potential energy is G M1 M2 by R. This is magnitude. It is defined for at least two bodies, right? This is the potential energy. Now, if you are given a chain placed at a height h from the surface of the earth, what is its potential energy? In this case, it is mgh. But sir, you said potential energy is not defined for a single body. Yes, here potential energy is defined for this chain and this earth. And this is only true. This is only true if potential energy on the surface of the earth, if we consider it to be zero, then only the potential energy of this is mgh if its mass is m and it is lying at a height h above the surface. Only if this condition is accepted, this is true. If this is not accepted, this is not true. Remember. Now, if you are given a chain, now hanging vertically, same height h, what is the potential energy of the chain if potential energy at here is 0? It is mgh. If your answer is this, that is wrong. The answer is mgh by 2. How? Now let me draw it like something like this. Consider, see, all the particles on this are not lying at a height h. In the previous case, all are lying at a height h, but in this case, all the particles are not lying at height h. Some are lying at 1 meter, 2 meter, 3 meter, and the maximum is h. Now consider a mass dm of thickness dx, which is at x distance from the ground. Now, du, small, potential energy of this particle is nothing but m, and this mass is dm. G, h, what is h? X here. Got it? Now, integrating it. Here x is variable, but we got it in dm form. We know that this chain is uniform, has same m by l value. So dm by dx is equals to total length. Total mass is m, total length is h, right? Now from this we get dm as m by h dx, right? G dx. Now integrating it, we will get U, potential energy. M and H are constant, G is also constant. Now let us draw it out. And X is from 0 to H. should integrate from 0 to h, right? Now, integral x dx, sorry, this is dx, integral x dx from 0 to h. Integral x dx is x square by 2, and this would be mh by mg by h into h square by 2. So this would is mgh by 2. So should we do all this for each and every problem? No, I'll show you a shortcut. At every time when you are asked the potential energy of an object, then immediately look at its center of mass. You know the basic definition of center of mass, where it gets balanced. In the next chapter, we'll be going to study in detail. In this case, the center of mass lies exactly in the middle. It lies exactly in the middle. That means it is at a height h by 2, right? H by 2, because it is same. Its distance is same from the top as well as bottom in this case, right? Its height is h by 2. So answer would be mg into distance of center of mass from the surface of the earth. In this case here it is h by 2. So it is mg h by 2, right? Now, imagine a chain placed on semicircular. Find its potential energy. I'll give you its center of mass is 2r by pi. Its radius is r. Now, its potential energy is simple. It is at a height 2r by pi from the ground. So its potential energy is nothing but mg 2r by pi. Simple, right? You can do it in traditional method also by taking a small element dx of mass dm and integrating it, we get the same result. We'll be deriving it in center of mass chapter. Now entering into the second type which we are going to learn, it is spring potential energy. This is simple. Remember that spring potential energy is always positive. It is always positive. Remember it. Now, consider a spring attached to some mass m. Okay, I'll draw it once again. Consider a spring attached to some mass m. It is at its equilibrium position. Let us take this as equilibrium position. This is a rigid surface. Now, potential energy, that means change in potential energy here is, if we move this block either to left or right, if we move block m of mass m to either to left or either to right, you will get potential energy as k x square by 2, where k is the spring constant. It is different for different springs, where x is the distance moved from its initial, we consider it as initial position where it is stable. If we move x distance to the right or to the left, it gains some potential energy. that is kx square by 2. This is also only true if we assume that potential energy at its mean position is 0. Let me move this to x distance and the object comes here. This is x. Now, this is final position and this is initial position. UF minus UI is equal to change in potential energy, which is kx square by 2. This is only true. The potential energy here is only true if its initial potential energy, that means when it is lying at its mean position, in stable position. If it is 0, only if we are assumed that it is 0 at its mean position, then the potential energy is kx square by 2. We can move it outside or inside. I mean expand the string or even contract the string. This is that. So potential energy of a spring is kx square by 2. Sir, you said potential energy is not defined for a body? Yes, here also it is not defined for a body. It is defined for a system. Spring block system. Understand? It is not a single body. It is a system of spring and this block. And also here we assume that mass of this spring is 0. Class 11 physics is all about assumptions. It takes many assumptions. See, this is a massless spring. Here we are considering the potential energy of this whole system, spring block system. It is kx square. As we said, it is always positive. See, k is always positive and 2 is a positive and square of anything is positive. So, spring potential energy is always positive. And if you are asked, if you move a spring from distance x1, if you move some more distance to x2 from its mean length, then you got to say the potential difference. That is delta U is equals to k by 2 x final minus initial, right? Final is x2 and initial is x1. See, initial potential energy is that here if we move this block to x1 distance from its mean position, right? Its potential energy is kx1 square, that is initial. And if we still move to x2 distance, then its potential energy becomes x square by 2, kx square by 2. And delta U, that is U final minus U initial, that is kx square by 2 minus kx1 square by 2. This is potential energy when you move the block from x1 to x2, where the distance are considered from mean path. And that's it.